Hello, my name is Josh Cramer, and today I'm going to be walking through my Transfer 1 Exam 1. So the question is asking for us to find an expression for the horizontal force exerted by water onto a dam. And so here we have two figures just to show what this question is asking, and we can assume the following things: that the atmospheric pressure is 0 atmospheres, that the equation pressure is equal to the density times the acceleration due to gravity times the height. We can assume that the density of water is 1,000 kilograms per meters cubed, and the acceleration due to gravity is 9.8 meters per second cubed, or per second squared. So to start, we're going to write that the equation for force is equal to the pressure times the area. And since we know that the depth of the water could constantly change, we do also know that the pressure at each depth would change as well. So we're going to change this equation into an integral to show that pressure in terms of area across the area. So what we can do is we can substitute the pressure here for the equation P is equal to rho GH, and substitute that into the equation. So now let's look at this drawing, and we can show that the area as a band across the trapezoid, and we can define the height of this band as dH, and we can define the width of that band as W. So what we can do is we can assume that the pressure at a given width is constant, and we can now plug this into our equation where the horizontal force is equal to the integral of rho GH is equal to the width times dH. Or I'm sorry, the rho GH times the width is integrated according to the height. So we do know that along this side of the trapezoid that the slope, that the height changes at a linear rate according to the slope. So we're going to solve for the slope, and we can show that the width at the height at the top of the dam, is capital T, and the width at the full depth of the dam is equal to capital B. And this demonstrates a movement downwards in terms of depth. So to find the slope, we're going to define the slope as M, and we're going to show that B minus T over H minus 0 is equal to the slope. So what we can do here is we can actually find an equation for the width in terms of the height as T minus MH. And we can plug that in for W in the equation. So what we're going to do is Fx, which is equal to the horizontal force, is equal to rho GH times T minus MH, and this H is equivalent to the height at a given point, times DH, and this is evaluated across the height of the dam. So assuming these values, we can plug these into this equation and move these two values outside of the integral because they're a constant, to show 9,800 times the integral. And I'm sorry, this is actually not the height of the dam, but actually the height of the water in terms of depth. And the equation, after we multiply this out, looks like this: TH minus TH squared DH. So what we're going to do is calculate this out, or we're going to integrate this. So 9,800. And the integral of this becomes TH squared over 2. And the integral of this becomes MH cubed over 3. And that is evaluated from 0 to the height of the water in terms of depth. So now we take that and we're going to evaluate these variables across. So we have the horizontal force is equal to 9,800 times, and we're going to evaluate this in terms of h. So we're going to plug in h to the h variable, and that just stays the same. MH cubed over 3. And then we plug in 0, but plugging in 0 just makes this to be 0. So now we have our answer. So the horizontal force in terms of the water onto the dam equals 9,800 times TH squared over 2 minus MH3 over 3. There we go. Thank you.